Welcome back, guys. Now that we've actually looked at the reader-writer lock as well as an application where we're going to make use of this, let's look at the sequential implementation before we dive into the multi-threaded one. So without further ado, let's go to the terminal and take a look at the code. All right, so I started actually putting this together. So you already have in here in this text editor a definition of an abstract data type called data. And data contains an array with 1,000 long. So 1,000 integer, there are 64 bytes each to actually hold the value. So this is the array that we want to use in order to hold the values of our prefix sum. Now, if we have that, then I have a little function here called silly, which takes as input two things, a value n, that is the a sub n that we want to compute, as well as this array data, which is embedded in our abstract data type. Now, the code is quite straightforward. If you look at it, it's going to be implemented recursively. And the base case is simply that the index you ask for is 0. So if you ask for the 0th index, what we're going to do in this case, and we're going to actually store, and let me put here the correct value, 0, right? The sum from 0 to 0 of the value 0, and that is what we write in the first entry. Otherwise, the inductive case is straightforward. It's going to go check and see that if the value is 0, it's going to call recursively in order to actually compute that. Otherwise, it's going to simply skip the recursive call and pick up the value in the nth minus 1 entry, which was non-zero, add n to it, the next term, and store that in the array at the offset n. Clearly, this should actually help us compute the prefix sum for our sequence, right? So, and if we were to call it silly 1023, it would fill up the entire array with all the prefix sum stored at each of the position. All right. Now, in order to actually do this work, do this computation, I have another helper function, void, that's called do work. It doesn't need to return anything, so I'm even going to simplify this a little more. I will have it return nothing, and this function is quite straightforward. It first uses the identifier of the thread. Even if we have no thread, there is at least one, right? The sole occupant of the process. So I'm using pthread self to get the name of that thread, is number. And I'm going to actually do a little bit of arithmetic on it by shifting and computing a modulo to get a value. That's the value, the index I will look up in my array, and then I make use of the silly function to fill up the array and pick up the value. Once that is done, then I actually simply return and say printf, and I'm saying, hey, it was called with this thread pointer, this name of the thread, and here is the value that I computed for the root, and the value of the root, the index, as well as the value for that index. So I will know we computed for that value, here is the result, and that was done by thread so-and-so, right? So I will have all the information about who actually did the computation and what that computation produced. Cool. So now that I've done this, I can actually have finally my main program, and we're done with this. The main program declares the data on the stack. So on my system stack, I get an array of 1023 long, which I initialize. Everybody's initialized to 0 in here. And then I simply do this loop calling 10 times do work. Why do I do that? Well, to actually exercise the code a little bit, it's going to repeat 10 times the same computation, not a very interesting one, but that's going to actually give us the foundation for looking at the parallel version. So now that we have that, let's suspend this. Let's compile this cache program. So it's called cache, and send that into an executable, and then we can run it. When I run it, you see what happens. It tells me, oh, I've been called by this thread. So you see that this time the name of the thread, the pointer I get back is 106D5CDC0. It was called, and I computed a value, 21, which means I want to get the entry 21 of the array, and the entry 20 21 is always the same. It's always the value 231. It's clear in this case that the first thread did all the work, filling the entire, or the only thread did all the work and filled up the array, computing all the indices between 0 and 21. I had a value in the index 21, then the other invocation done by the same thread also look up entry 21, and therefore as soon as they call, they realize 21 is already defined. I don't need to recur. I'm just picking up that value, right? And we're done with, this is a beautiful implementation. It's straightforward. Everything works as expected. That's it. That's what I wanted to show you. And of course, if I run this multiple times, you notice that sometime I'm getting here that because the name of the thread was different, the modulo he computed is 0, and therefore he got entry 0 of the array. If I run it again, because again, the address of the thread, that unique thread, has changed, then the index that we want to compute is changing. So there is some random behavior because I'm using the identity of the thread, which changes with every run of the program, in order to compute the value that I want to pick up from the array, right? To actually come up with a specific seed in a sense. I could fix the seed as well, but that's going to be useful to actually do that in parallel so that all our threads are asking for different values. That's it. That's what I wanted you to see at this point. We have the sequential code. Now, next episode, we need to start, and that's going to take us a little longer. We need to look at the recursive code that does that in the context of multiple threads. So we will set up the threads and then we will upgrade our implementation so that it reflects our needs. But that we'll do next time in another video. Bye-bye.